We are up and we are recording. Excellent. I suppose you guys are able to hear me clearly. Welcome back from a very short Wellness Day break. I hope you guys had the chance to relax, take a bit of a break from online classes. And now we have our batteries recharged to take us through to the end of the semester. And it's going to be easier this time because the weather is cooperating and everybody is sort of going to be in better spirits. So I think this will go well. Colin says I just used it to work on circuits. Okay. All right. So what are we doing today? We are going over daily quiz number 19 for your attendance. That is due midnight tonight. So please go to Gradescope and answer the 4 multiple choice questions for daily quiz number 19. Today is Friday, April 9th. The homework that is due tonight is homework number 10. Homework 11 will be posted later today. It will be due Friday of next week. The studio that is due tonight is Studio 6. Many of you have already finished this, but those of you who haven't, you have the help sessions organized from 6 to 10 p.m. today. So take advantage of that and submit your work by tonight, April 9th. Studio 7, which I believe is a very exciting studio because you can give your own spin to the outcome of Studio 7. So I've seen students kind of get very creative, very excited about the fact that they can get their own message to scroll on the 4/7 segment displays. Some of them have used it to convey a personal message to their loved ones. Some of them have displayed some funny messages. While you work through Studio 7, which is due April 21st, so you have some time to do this, think of a very interesting message that you want to show, and then maybe you can take a video and pass it along to a loved one. All right. In terms of studios, Studio 8 is going to be our last studio. Studio 8 is again going to be a LogicWorks simulation studio. So you have another week between 21st and 28th to complete that Studio 8, which is going to be a elevator controller design. Okay, so that's what we are looking at. Now, let's take a look at your exam 2 statistics. The very positive news in terms of the grades. 38 students have scored above a 91. There is 72 students above an 81. So that's a very, very good news. It looks like you guys have worked really hard and paid attention to the content between exam 1 and exam 2. You can see that skew, a negative skew in the grades when you look at the median of 87, while the average of the exam was an 82. There were a few students with the total score 101. They scored all of that. Standard deviation was high, a 17.27. There were a few students below a 50 point mark, which is very concerning. And we have one more exam, our final exam, to sort of make that adjustment so that we get a passing grade for the class. So please use my office hours. Please come and talk to me about what you can improve, what material you need to concentrate on, how do you prepare for this upcoming final exam. Let's come up with strategies together so that we have an improvement in your grade. But other than that, it's positive news. It looks like you guys liked the fact that there were no multiple choice questions, and that they clearly sort of reflected in very high grades. Now, what I want you guys to do is this: look over your grades, look over your graded So Bennett says design-based questions were great. That's really good to hear, Bennett. Um, the challenge in terms of design-based questions is that the design has to be complicated enough for you guys to get interested, and it cannot be simple enough for you guys to go through it very quickly, right? So it has to be that right balance. The multiplexer was absolutely terrifying. All right. Oh, nice. Great. I'm glad to hear that you found the exam to be very fair. Um, Excellent. Marks ended up being kind of yeah. So you see it that was the intention, right? Like if you start thinking about it, you sort of get intimidated, maybe get overwhelmed about the number of choices that you have because there are so many ways to do it correctly. But at the end, as you spend more time with it, as you think more about it, it turns out to be a very very simple problem. All right, let's talk about what I want you guys to do. Look over your graded work, please. So look over your graded exam 2, and then if you have any regrade requests by email directly to me by April 16th 11:59 p.m. So you've got 1 week to apply for regrades. Look over the solutions, look over the rubric, look over things in detail, and then if you have concerns, clearly those concerns in which there was a misclick by the TA or incorrectly marked answer, you please bring that to my attention. And for that to happen, you have to go over your graded work. We didn't get Facebook for an answer though. Come on, I tough crowd, man. Come on. All right, that's as far as um and like Andrew says, he had a situation with misclicks. So yes, please check. All right. What else do we need to talk about over here? High average, yeah, even higher median. Most of the classes, doing pretty well. And I talked about the concerning aspects already. So I think that's it for this. So for those of you who are you know already there, you got to try to stay up there for the final exam. And for those of you who are over here, you're going to try to move up there, right? So that should be your goal moving into the next 4 weeks of the semester. Speaking about the last exam, your final exam, it has been scheduled by the registrar on this May 11th. That's a Tuesday, between 3 to 6 p.m. Eastern time. So I'm going to be, giving you guys details about the logistics, how the final exam is going to be run as we get closer to the final exam. But that's the day we are going to have it on, Tuesday, May 11th. So please mark your calendar. Have nothing scheduled on that day, especially in the afternoon. Okay. Mark your calendars. Uh, is it 11:30 to 2:30? I have two exams that same day. I might have mixed it up. Is it 11:30 to 2:30? I have two exams that I'm giving on the same day. I might have um, gotten the timing wrong. I know it's the same day. At least on the screen it says that. All right, let me, well, all right. So yeah, let's put this one. Need to check maybe 11:30 to 2:30 p.m. Yeah. Yeah. So okay. So if if the schedule says 11:30 to 2:30 p.m., then that is it. This might be the time for my other exam. So cancel this out then. Sorry about that. This is the time we are going to have the exam on. Imagine missing the final because you thought it is. Well, all right, guys, hold on. Is it 3 to 6? All right. Bennett says 3 to 6 p.m. It looks like it was 3 to 6 p.m. Okay. All right, guys, it looks like it's 3 to 6 p.m. So this was correct. But, whatever the registrar document says, right? I think it says this. Moving on. We were talking about counter application. Correct all along? Yeah, I know. I don't usually miss such things. But anyway, let's take a look at this. We have a counter design in which this is something that we already did, right? Start counting at 3 and then stop counting at 12. So what we did was we tried to detect 12, and the moment we got 12, we loaded 3 into our counter, right? So we detected 12 as the counter output by using this 2-input NAND gate. And wherever there was a 1 for 12, it was 1, 1. The two most significant bits had to be a 1 for the 12. We put those two as the input of the NAND gate, and the output we connected directly to an active load input. Right? So whenever we detected 12, we sort of loaded 3 into the counter, and we loaded 3 into the counter by connecting A, B, C, D as 1, 1, 0, 0, right? So it's A is the least significant bit here. So it's going 0, 0, 1, 1, right? A is the most significant, D is the least significant. We have talked about this in the previous lecture, but we loaded 3 into the counter whenever we detected 12. So that's where we stopped. Now, the next thing that we are going to do is we are going to see how we can cascade these 74163 chips in order to build bigger counters. Now, as you can see, we have a common clock, right? So this clock signal is triggering the first chip as well as the second chip. So the first and the second chip are being triggered by the same positive edge of the clock. So it's a positive edge trigger design here. We have an active low clear connected to both of them. The same signal is being connected to both of them. Active low. The same load, active low load, is connected to both of them. Then there is a counter enable signal that we are connecting to both our enables for the first one, and we are enabling the second chip by using the ripple carry output of the first chip, right? So whenever we reach 1111, this guy is going to become active and it is going to enable the second counter. Now, in terms of an arbitrary value that we can load into this counter, we have D0, D1, D2, D3 for the first chip, and then D4, D5, D6, D7 for the second chip, right? So we can load any value between 0 and 255, right? So we can load any value between 0 and 255. So this essentially means I can start at any value there. Ohm says, I'm still a little confused why there are two enables. What does ENP and ENT stand for? So there are two enables. One enable specifically, ENT, is being used along with the ripple carry output. So for example, if I go back here, let's see, where is that? No. So when we were talking about the properties of this chip, we said there is a slight difference between the two enables. The ENT goes along with even the RCO output, which means the RCO is asserted when the count reaches 15, but also at that time, one of the enables should be asserted. So that means that if the count is 15 and enable P is not asserted during that time, RCO will not be asserted, right? So there's slightly a different use of those enables that will essentially help with cascading of those chips, right? I can put more and more together if I need to. That's the only difference. Let's go back to this. Where is that? Right here. Okay, so I can load any value, right? 0 to 255. All of those. Matt says, should we think of these counters as having no propagation delay? No, there will be some propagation delay through it. And it will be reflected in the timing diagrams. But right now we are assuming that the outputs of these counters, Q0 all the way to Q7, these are changing soon after there is a positive edge on the clock, right? So soon after. So if you want it to be very, very specific, we could say the outputs of the counter, all the Qs, would change after the propagation delay of the 163 chips. Right? So that would be a very specific answer there. But right now we are assuming that we are changing soon after there is a positive edge of the clock. So we are leaving it as soon after, not talking about an exact propagation delay. But in reality, yes, you're absolutely right. There will be some finite, small propagation delay through these chips. But if you notice, because the clock is connected to the same clock is being connected to both the chips, all the outputs are going to change at the same time. Right? So all of these guys and these guys will have the ability to change at the same time. Because if this guy has a propagation delay, it will be the same as this because it's the same chip, right? Even though it might not be exact, but it will be very, very, very close. All right, so I can load any value into this counter that can be between 0 and 255. What is the maximum value this guy can count? Let us try to write that over here. So this can be 1, 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 right? So that would be all 8 ones. So Colin is right. 2 raised to 8 minus 1 would be the highest value it can count, which should be 255, right? So I can use this to count from 0 all the way up to 255. But, you know, so how am I going to 255? Let me talk about how we are using this ripple carry output here. When you connect this ripple carry output to the two enables of the following chip, What you're really doing is every time you reach a value of 1111, which is 15, you will increment this guy by 1, right? So when you reach, every time we reach, when we reach 1111, which is essentially 15 in decimal, we will increment this guy by 1. Increment then the next 4, right? So that's Q7, Q6, Q5, Q4 by 1, right? Because that is the only time this guy gets enabled, and soon after that positive edge, it is going to go up by 1, right? That happens only when this guy, all of those are 1111, which is essentially going to set up your 8-bit counter. So if I add this here, show you guys how this is working. So you have, say, Q7, Q6, Q5, Q4, Q3, Q2, Q1, Q0, right? So the low 4 bits are output of the first 163 chip, right? So that's your output of the first 163 chip. And then the next 4, Q4 all the way to Q7, are the outputs of the second 163 chip. And this guy goes 0, 0, 0, 0 all the way to 1, 1, 1, 1. And during this time, let us just assume that all of these guys are 0, right? So these guys are going to be all zeros. They do not increment because it has not been enabled yet. But when it reaches 15, you see this? When it reaches 15, this guy gets enabled, and then the next positive edge you see, all of these guys will increment by 1. Right? So the next value here will be, this guy will increment only by 1, and then these guys go to 0. And then 1, 1, 1, 1, right? During that time, it will still be there. So that's sort of your second sequence. Second sequence of 16 counts. Followed by, this guy again gets enabled. So all of these go to 0. And then this will increment by 1. You see that? And then again, this will go sort of to all that, right? And this pattern keeps on going. And if you now zoom out and take a look, what we really have is a 8-bit counter that is happening over here. This guy is changing the fastest, and then that, and then that, and then so on, all the way up to Q7. All right, so that's how we are using this ripple carry output over here. We are not using the ripple carry output of the second chip. We could, if you wanted to, if you wanted to find out when we reach 255, we could use this RCO as well. All right, now I want to do some sort of, an interesting task here. Let us say, what should I do if I wanted to count from 60, 61, 62, all the way to, say, for example, 128, right? What should I do if I want my design to start counting at 60 and stop counting at 128 and go back to 60, right? What should I do then? Any ideas? Think of it as this statement. Think of it in terms of this statement. Load 3 into the counter when 12 is detected, right? As simple as that. Load 3 into the counter when 12 is detected. Jeremy says load 60 into the counter when it reaches 128. All right, perfect. That's exactly what I was looking for. Now tell me, how do you detect 128? What would be the simplest way of detecting 128? Load 60 when RCO is 1. But RCO is going to become 1 every 16 counts. Q7, that's right. Q7 is 1, right? So Q7 is going to be 1 when you reach 128, right? So because 128, let me sort of write another one here. After current So I say 128 in decimal is going to be 1 followed by all the zeros, right? So Q7 is a 1 there. That's it. That's the only one there, right? And at that time, I want to load 60 into my counter, right? So what should I do? I need to look at on the second one, Q7. That's right. So I'm going to take my Q7 and I'm going to sort of load, and I'm going to connect this to my load input, right? And on purpose, I've done something wrong. Is this going to load when I have 128? No. What else do I need? It's an active low. That's right. So I need a NOT gate in the middle, right? So I need a NOT gate because it's an active low input on the load. All right. So I'm going to erase this a little bit and say, okay, let me put a NOT gate here. All right, I'm done, right? So whenever Q7 becomes a 1, you make load 0. Whenever you have that load going to 0, it's an active low input. It is going to override the counting and it's going to load whatever I connect to the 8 inputs, right? I don't know that yet. I need to do 60, right? So what is 60? Let me go back here and try to find what 60 is. 60 in decimal. What is that in binary? So I need 32, I need 16, I need 8, and I need 4. So that means I need 0, 0, then 1, 1, 1, 1, and 0, 0, right? So that's what I need for D7, D6, D5, D4, D3, D2, D1, and D0. So that's what my 60 is going to be. You have connect Q7 to the load on the second one as well. Only for the second one. No, only for the second one, right? Apart from that, it is going to continuously count. Oh, yeah, you're right. Oh, okay, sorry. You guys are absolutely right. You guys are absolutely right. I need to do that loading. At the same time. So let us put my NOT gate somewhere here. And then I think I'm ready to load, right? Take a straight line and jump to this. Okay. Then dot and dot. All right. Perfect. I think this is good. Yeah, it wasn't okay before because we were only loading a new value into the first one. We have to load the both the values, right? We have to kind of load 60. So I need some here to go into it, some here to go into this, right? So we were only doing the first part. We were not doing the second part. Isn't the load going to both? Yeah, that's right. Either way works, you guys. It's already connected from here anyway. But if you look at this, this is sort of very clear that both are connected. All right, so what are we loading? We are loading 60 into it. So what is 60? 60 is all of these, right? The middle 4 bits are 1, everything else is 0. All right, so let's do that. I have 0, 0, middle 4 are 1, and then 0, 0. You guys see that? All right, so this is loading 16 to the counter whenever you detect 128, right? And clearly when you have a random power up, it might not be the case, right? If your counter randomly powers up in a state like 129, then it will load 60 into it, right? So it is possible that for the at least for the first cycle, it might not do 60 to 128, but eventually it will fall into that region. All right, questions here? The modulo for this counter is 69. This is 64 plus 5, 69. That's right. 16 modulo 69 counter. If you are doing 0 to 255, that's a modulo 256 counter. And obviously we need 8 bits for doing that. And 60 to 128, that's your modulo 69. When RCO hits 1, does QA go to QD, go back to 0? When RCO hits a 1, QA goes to QD. No, QA through QD go back to 0. Kang, I'm not sure if I follow this. Yeah. So whenever the counter is counting, right, it by default goes from 1111 to 4 zeros. So the overflow bit is okay, great. Yeah, so it'll go from 1111 to 0000. All right. What if we wanted to stop at 129? What if we wanted to stop at 129? What would we do? Q0 NAND Q7. You are absolutely right. So you would take Q0 from here and you would take QD from here. You would put them through a NAND gate and then load 16 to the counter. You guys see that? Just as we did over here. Whichever bit is 1, you would take that and then you would put a NAND gate to detect that essentially, and then put it to a load input. So I suppose with this example, with this circuit, you guys are now able to think of all the possibilities here. You can start at any value between 0 and 255, and you can stop at any value between 0 and 255. The only constraint is that it counts up only, right? It doesn't have the ability to count down. It only counts up. So it would be useful to have a counter that can also count down. This guy can only count up. Let me just write the answer here. Use Q0 NAND Q7 to load, right? Both chips. That's sort of the answer for 129. This was tricky on the homework without the gates. Yeah, but you're almost. It is tricky, yes. But I think after this conversation, I think you're going to be very close to the answer, because all you need is great. That's nice. Okay, questions about this, guys. How do you use two 163 chips to start a counter at any value between 0 and 255 and stop it at any value between 0 and 255? All right, so now let's take a look at another example here. We are using the same 163 chips here. This is already configured using some logic gates. For example, we have a 2-input NAND gate over here. We have another 2-input NAND gate over here. And this is a modulo 193 counter. So what we'll do is we'll try to find out the start and stop value for this, right? Like where is it starting and where is it ending? Start and end. What is the starting value of this counter in the sequence, right, in the pattern, and where is it stopping, where is it ending? So to find the start value, all I need to look at is what am I loading, right? What am I loading? So because you see this, this RCO is being used to enable the next chip, and what we are doing is we are using this reload signal to activate the load input of both the chips. So by looking at what are this A, B, C, D and what are this A, B, C, D signal connected to, inputs connected to, I can find out what am I loading when a desired value is detected. I don't know what that desired value is yet, but let us see what are we loading. What are we loading? All of these are 1, 1, 1, 1, right? These are 1, 1, 1, 1. Those are all connected to high. And this is 1 and 1 and 0 and 0, right? So what we are loading into the counter is 0, 0 followed by all ones. And if you convert that to a decimal value, it should give you 63 in decimal. So we are starting the counter at 63, and let us see where we are ending. Well, all of these are not being used for detection. These are just the 4 least significant bits of the counter. They are left unconnected. They are just our output. Q4, Q5, Q6, Q7 again are left unconnected. Those are just the 4 most significant bits of the counter. And we are only using sort of this RCO of the second one, which is essentially saying that I have reached the maximum count, which is 255, to go back into our counter to eventually activate the load signal. Along with, there is a go input as well, which is essentially saying, okay, now you can count or you cannot count. Sort of the enable for the entire design. So what we are really doing over here is we are reload 63 when the counter reaches, what is that, 255, right? Because at 255 this guy becomes a 1, and at the same time your go underscore L should be active. So if you reach 255 and your go underscore L is also enabled at that time, you are going to reload 63 into your counter because you have already hardwired those signals. And all the other things apply. They are both connected to the same clock, right? The same clock is being used to edge trigger both of the counters. The clear is the active low input that is connected to the same input here, reset underscore L, for the entire design. That can be used to initialize it to all zeros, all 8 being 0. One of the enables is the ENP. ENP is connected to this counter enable along with the same ENP on the second chip. The only thing that we are sort of playing with is RCO is being used to connect to the other enable here. So what is the end count? Well, clearly that should be the maximum count, 255. And if you see 63 to 255 gives you a 193 different states. So that's your modulo 193 counter. Is it the only way you can design a modulo 193 counter? No, you could have gone from 0 to 192, right? So you could have also done 0 to 192. How would you do 0 to 192? Ideas? 192 is 1 1 followed by all zeros, I think. Yeah, I think 192 is this. 128 plus 64. Right? Yeah, 192. check for 192 and then clear. Perfect. Check for 192, which is these two guys, right? So you can take Q7 and Q6, these two guys, Q6, Q7, and then connect this to your reset underscore L, right? The moment you reach 192, it is going to reset it to all zeros. That's another way of designing a modulo 193 counter. So I suppose you guys are now getting more and more comfortable with, playing around with different counting sequences. What would be the functional difference between a modulo 193 like this and 0? Now, no difference. It's just that one starts at a 0, one starts at 63. So it's totally up to the user to do that. This guy uses one NAND gate. This guy uses a few more gates. There's no functional difference. One guy is using the load, one guy is using clear. If there is any difference, I would say it is this: the fact that load input overrides counting, overrides the enables, and clear overrides load, right? So right now we are using clear in this one, which is going to override the load input. That's sort of the only difference there. So we talked about it over here. So these are in the notes. If you guys want to refer back, load is a load overrides counting, clear overrides loading and counting. So these are already part of the notes if you guys are interested. All right, questions here. Would the counter be able to load even if ENP was inactive? Yes, it will be able to load, but it will not be able to count. All right, now we will go on to our next chip, which is used for counter application, which is the 74X169 counter chip. This can go up as well as down, right? So a little bit more interesting here. But in many aspects, it would function the same way as the 163 chip. We have a positive edge triggered clock, right? So it's still counting up or down every time we hit a positive edge on the clock input. Then there is an up and down input. So let's talk about that. Up or down input. So when it is up, when it is 1, when it is connected to high, we will be counting up. Just the same way as we were doing for the 163. But when it is low, we will be counting down. From wherever it is right now, the counter value, it will count down from there. And then we have, an active low load, then we have 2 active low enables. And then we have 4 inputs that can be used, that can be used to load any arbitrary 4-bit value into the counter. 4-bit value into counter. Any value between 0 and 15 you can load into the counter by using those 4 active high inputs. And then at the end we have at the output side we have 4 active high outputs, which are essentially saying what is the value of the counter, right? Value of counter. And then we have a active low RCO output. Active low RCO output. And it works differently D is the least significant or most significant. Okay, so let me just check. It is going to be the same as before. 0 is 0. So D is the most significant. MSB. Is there a reason to use 160? Up and down. That's it. 169 gives you the ability to go up and down both. 163 can only count up. Well, sure. You're right. 163 can do only up and 169 can do both. Load seems very easy with this. 160 is probably cheaper too. Yes, yeah. More functionality means more hardware, more expensive. All right, let me talk about this RCO output because it's different for 163 and 169. So when you're counting up, if you are counting up, RCO becomes active when counter reaches 1111, all 4 ones. And then when you're counting down, let me just copy this and remember RCO becomes active means it's an active low output, so it becomes low. Counting down, RCO becomes active when the counter reaches 0000. Is there a way to set the increment to anything other than 1? No, the increment value has to be a 1. The increment is always 1. For that, you might have to design your own counter, which we will do just, in a minute. We will get into that. All right. So up and down counter 74169, RCO is working slightly differently. It becomes active at 1111 when you're counting up. It becomes active at 0000. By the way, these are over here, right? Let me color code this differently. Blue. That is talking about these. The outputs becoming 1111 or 0000. So slightly different times it is going to become active. But yeah, that's it. Now you can use this in the same conversation as cascading counters. You guys see that? So I hope now you can see that when we were cascading 163 chips, we said we can start at any value and stop at any value while counting up. Now we should be able to say I can start at any value, stop at any value while counting up or down. You guys see that? Similar mechanics to how we cascaded 163. Detect some value and then load whatever you want to start it at while playing with that up and down input. All right. So that's all I have for the counter application discussion. I'm going to stop recording here.